Um, yeah. So just a rough timeline of what we'll be doing today. First, we'll just go through how, like, what's in the paper in terms of the methodology and stuff for around half an hour. Then we'll kind of go through a bit through their code base, not a lot. And we'll also see a demo. They've kind of there's a Hugging Face demo which is available on Hugging Face Spaces. So we'll just go through that as well. So yeah, let's start off. Of course, just for an overview of what this is about is that in diffusion models, we've got like if you're talking text to image diffusion models, we're talking about having a prompt in the sense some text input, whereas like prompt engineering, as many of you know, is itself a difficult task because there's quite a lot of effort which may go into that to get the perfect uh, output for whatever prompt you're passing. Secondly, this has been said many times, like an image is worth 1,000 words, so it's very hard to describe the specifics of an image by just describing the text if you want any specific changes in the image. So if you want to avoid having to do the tedious task of engineering the prompt, you could just do something simple to passing some visual representation of what you expect of the model and use that as the conditional signal for denoising. So that is basically what this paper is about. Um, so just a bit of background knowledge on diffusion. So diffusion is just a Markov process where we have we there's a noising process and a denoising process. The noising process is performed in a series of Markov steps. Like it's a Markov chain of steps where we add Gaussian noise to the original signal for a fixed number of time steps, which you sample during training, according to a predefined variance schedule. So the beta you're seeing in the equation at the in the noising section, that is the variance which you've kind of defined, like based on the schedule which you've picked, which can be square root and so on. And then you add noise for a sufficient number of time steps, and then you perform the denoising process, which is done with the help of a probabilistic model. So the theta you're seeing in the denoising equations, that's the parameters of the model which you're using for denoising, and then you use that model to denoise the noised signal into something else, and you compute the loss based on the original signal and the one which you got in the output with the help of a variational bound with a on negative log likelihood. So yeah, we'll go into the loss function a bit later. They've kind of opted for the same loss function as the DDPM paper, the original one which came in 2020. So not a lot which they've attempted for that part at least. Um, yeah. Now we'd go into some of the like categorizations which they've made to where they kind of compare their approach with the others. So the first categorization they've made is the image variation models, i.e., all the text to image diffusion models which we've been seeing over the past year or so, which includes Jiayi, Imagine, and Stable Diffusion, and all of those. Uh, I've just kind of tried to represent it as a general process, so that any of those models would kind of fit into this. So initially, the input obviously is text, where you pass it through some encoder. Now this can be any encoder based on the method. For example, DAL-E opts for a clip based encoder, whereas Imagine, for example, opts for a frozen T5 transformer, T5 XSL to be specific. And there are various other methods, like various other encoders which are used. Some use auto encoders and so on. So I just to not fixate on a particular encoder, I've just mentioned it to be a some encoder through which you get some textual embeddings. And then again, you apply some model which is there to kind of map it to an image space. So the space of the image which you like, space in terms of the image output which you want. And once you've done that, you just use a diffusion decoder to kind of uh, do the denoising process, as I mentioned in a couple of slides before, where you have this probabilistic model which you go on trying to denoise it to like subject to a variational bound loss on the negative log. Yeah, yep, yeah, Samaya. Um, would you like to say something, or no worries if the hand was raised by mistake, that's fine
Okay,
as well.
sorry.
Yep,
I have a question about the
yep,
diffusion decoder. Uh,
yep.
it's trained on a noise. How does it know to transfer this knowledge to text? Like if
So, yep. So it doesn't transfer knowledge to text. Actually, we use text. So the data sets which are mainly used for training this one, these kind of models, like the ones which you're seeing on the slide, those are basically have text image pairs. There's a number of those. In fact, this paper as well.
it's like fine-tuned on text.
Uh, Not fine-tuned on text. Like it depends on the approach which is taken. If someone is, if there's an approach, like for example, if there's a pre-trained frozen model which is used for getting those textual embeddings, then no. But in case you're training that model, then you are training from scratch as well, based on the data set which you're using. So basically, you pass that text, you get those embeddings, and then you try to compare the image which is generated through the whole process with the original one based on the log likelihood which you compare, basically from the original one to the generated one.
Does the diffusion decoder come from come pre-trained, or do we train
No,
it again
yeah,
in
yeah,
this
yeah, the diffusion
in this
decoder is trained.
process? It's trained again, so it's
Yeah,
not
it's trained
related.
altogether. Yeah.
It's not like pre-trained on a diffusion decoder and encoder like the last slide.
No, no, the encoder might be pre-trained, but the decoder, from what I've seen, mainly is trained. Sometimes you start from a kind of a pre-trained one and then you fine-tune as well. But
Mm.
the decoder is obviously a trainable one, basically. The parameterized model which I talked about when you do the denoising process, that is basically what we're talking about when you in terms of the decoder.
So here it just has the same structure, but it's trained on text.
Not necessary. Like in terms like I'm not sure which you're referring to for the same structure.
Just my
Yep.
the thing that I not understand is that if the diffusion decoder is trained like in the last slide, if there is an encoder and then a decoder,
Yep.
and then we take the decoder after training in the same manner like of the last slide and put it in this model.
These two are basically pointing to the same process. Basically, like it's not like we trained this and then we went forward. This is kind of a representation. This is just a basic representation of what diffusion is, and this is just a representation how you train it for text to image generation.
So is the test? Okay. I think I get. Thank you.
Yeah. Yeah, probably the way I arranged it, probably you may have thought that that is the first step and this is the next one. It's not the case.
Okay.
Yep.
Thank you.
Yeah. So just to get back to the point, this is not like I've not tried to explain for a specific text to image model because like that's not the scope of today's talk. But basically, this is the process, the general process, and then based on the like different approaches which are taken, try to use different encoders and different models with the same pipeline, basically. So yeah, let's move forward. So this is the second categorization which they had made. So where you kind of try to fine tune a model based on a particular subject. So for example, there's this paper called Green Booth by Google, where for like as you can see from the image, you've got a ton of images of a dog, and then you use these images and you based like once you've used these images you've passed to the model, then you just pass different prompts and it uses this particular structure of a dog in those contexts. In like on a high level, that is basically what happens. Internally, they're basically converting it to an embedding and they're assigning an ID to it. And then when you pass a particular prompt, it's using that ID to get those representations before you do the decoding. Yeah, Abhimanyu?
I'll be quick. Like
Yeah,
the embedding space these text to image or
yeah.
basically edit models are using, is it a shared space between image and text, or is it like one or the other one? Just
It again, it depends on the process which is used. Like for example, if you're talking about DAL-E, from what I've understood, it was kind of a clip model. Basically, kind of they trained a clip model which used to just take. No, they didn't train it. They used a clip. They used the clip model. Basically, would take the textual input and convert it to image embeddings or something like that. It wasn't really uh, like the text and image embeddings aren't exactly the same.
okay. I just so like okay.
Yeah,
I'm not sure actually, like because
yeah,
let's suppose you have a text
yeah,
and you want to synthesize image from that.
yeah.
So if you're using embedding, shouldn't that be a shared space between both of the modalities? Like
Okay,
in
yeah.
order for you. Hmm?
Oh, okay, yeah. I get what you mean, but basically what I'm saying is, when you pass text to it, it doesn't necessarily have to point. Like at some point, it will. Before you do the decoding, you obviously want a particular representation, which you get from the text, which you can consider as a shared one with the image representation. But what I'm saying is uh, like if if you use a pre-trained model for it initially, and then you use another process to convert that to an image space, then both of them may not have the shared space at the first step.
Oh, okay, I got it. So it's basically you're
Yeah,
using a sequence to sequence model where the encoder basically encodes your text into a hidden dimension, and
yeah,
the decoder decodes that hidden dimension
yeah,
in some way to a visible image.
yeah,
But as you train those that whole system, the hidden space itself becomes a multi-model embedding dimension, which basically is like common for text and image, sort of like that.
yeah. I mean, the way I have thought of this is like we just use some intermediate model to convert it from the text space to an image space when you get the embeddings.
Yeah, yeah, I got it. Okay.
Yeah, sounds good. So as I mentioned, this is the second kind of categorization they made in terms of controlling the output, where you'd kind of pass certain images of the entity you want to represent. And basically, as you can see in the image at the bottom as well, you're assigning an ID to it, like V in that case for the dog. And then you would just pass certain textual inputs by using that ID to, in a way, you're trying to embed that object or that entity into the context which we are referring to. So that was the second categorization they had made. Uh, so the third one they made, the third categorization is not really kind of specific to diffusion models, but this is something where uh, we just use an exemplar as a condition to convert some structural representation, which could be a mask, which could be the edges or something like that. You just convert that structural representation into a photorealistic image based on some exemplar which you're passing. Now, this is not specific to diffusion models, as I said, but they've also tried to derive from this process to kind of get the approach which they have. So this is kind of an example of what it looks like. So for example, if you're talking about control net, basically the process, like the original network is as it is, but you just take the input representation, you pass it through another trainable model, which you would assume to have certain control signals in the output, and then you would just combine that with the original one but when you pass the loss, so that you kind of try to tune it in the direction of the control signal which you want your model to be trained in. So that's kind of what control net tries to do. Whereas this T2I adapter basically just uses some conditional signals. So what they were trying to achieve is that they assumed certain implicit signals inside that image, inside that representation, which the intermediate representation which they created. They assume certain kind of control signals and which were implicit, and then they just tried to use them explicitly to condition the output, basically in the second one. And on a high level, basically what we're doing is we are trying to use certain structural aspects of that particular image which we want to control or we want to restrict to, and then we are using an exemplar to condition what how we would convert that to an output, which is which is kind of the approach which they've taken in this paper as well, which we'll see in the demo too. So yeah, this is kind of a general inference which they've drawn from the categorization they made, that you know, text, like directly trying to map from a text space to an image space, they feel like it is not sufficient in terms of the information which you want to convey. So yeah, and this is the comparison which they made. So in terms of the 5 categorizations which I referred to, or 4 of them actually, we went through 3. The 4th one was just prompt engineering, which we talked about at the start. And this is the approach which they take, which we'll go through now. Yeah. So in their approach, what they're saying is when instead of using text, you just use some reference images, which could represent anything related to the output. It can be a simple scribble of that particular image. It can be a canny representation of that image or anything like that. And they just designed an encoder for themselves, which they're calling C coder. And they're trying to replace the clip encoder, which, for example, was used in DALI. So that C coder would just take in multiple resolutions of different kinds of representations of that image. As I said, it can be it can be a scribble, it can be a canny representation, anything, and it would generate a visual vector to represent that particular reference image. Or those reference images, and then you would just kind of plug in into any diffusion model which you have. Like the one which they've shown at the bottom, it can be any of the diffusion models. You're just kind of using this C coder to get those reference images into the space which you're trying to decode from. And yeah, this is the way the C coder was designed. So they've got 3 sections. So the encoder, then there's a decoder, and there's a query transformer. So as you can see, the encoder is just kind of extracting feature pyramids from the image. Then the decoder is trying to convert them into multi-level image representations. And then the query transformer just attends to all of those representations to generate a single vector to represent represent that image or the reference image which you're using. And yeah, this is just kind of going into a bit of the details. So the decoder is obviously a transformer-based network. So you just go over all the features, convolve over them, like all the feature pyramids which you've got, and then you just concatenate and pass it through the attention mechanism and convert it back to 2D. And the query transformer obviously converts all of these visual features into a single embedding, which then you pass into your diffusion model. And this is just the thing which I mentioned before. Like they've just tried to use the loss function from the original paper itself, where you just try to apply a variation lower bound to the negative loss likelihood. And the data which they've used is like this. These data sets are basically image to text data sets, but for training, they've just used the images from that data set for obvious reasons, because it's prompt free. And these data sets were actually the ones which were used. Like, for example, this was used for DALI, the first one. And they've just tried to demonstrate that they can get competitive kind of results using the same data sets. So yeah, I think that's kind of it for in terms of the process. Probably we can go a bit through the code which they shared as well. So I'll just stop presenting from here and just share the other window. Yeah. So their main contribution in terms of the code is just the C coder, because they've also mentioned in the paper that you can just use it with any existing diffusion process. So just with the input reference images, and as a result, we'd go through the decoder first. As I said, there's three main layers in it. It's the encoder, the decoder, and the okay, hold on. The encoder, the decoder, and the transformer, the query transformer. So obviously, this is the just for applying the convolutions inside the decoder. And this is just the general multi-head attention layer inside the decoder, where you kind of stack a number of layers, and then the attention mechanism, again the same one. Then cross attention is applied for when you have multi-level visual representations. You're applying cross attention across them in the query transformer, and that's why they've implemented that too. Then just the feed forward layer. And then you have the decoder, which just kind of combines all of these layers which were provided. So we want to apply a convolution as well. And then like you want to apply convolution, then you want to kind of flatten it, and then you want to pass it through through the multi-head attention. And this is the query transformer, of course, where you just have alternating self-attention and cross-attention layers, and followed by a feed forward layer. And yeah, and this is just kind of a high-level representation, like you have the encoder, the decoder, and the query transformer. So yeah, this is kind of their main contribution. The rest seems to be code which is present in almost every diffusion code base, in terms of the schedules and transformations and stuff like that. So there's also a demo which is available. I'll kind of go to that now. Yeah, so basically, as you can see, you have a reference image, and then you have a certain representation. Like this is the reference image, and then you have a certain, you have the original image, and you kind of represent what you're expecting of the model in some way. It doesn't necessarily need to be a specific image. Like it can be a canny representation, can be scribble, can be a depth representation, and so on. And you can just pass one of those, and it will try to. Okay, how does this get selected? Oh yeah. So for example, you had this image here, and then you just kind of scribbled around some kind of representation which you expect, and then it tries to use that representation, which is passed through the decoder, to get some representation of it, and then the original image is kind of converted to this one based on conditioned on these embeddings. So there's quite a lot of things which they've tried out. So for example, this is a depth image where you just kind of show like the orientation of the two cars, and then it uses the original one to get the other one. And there's also another, there's the open pose. Okay. Yeah, there's the open pose representation as well. And obviously there can be any number of representations, which totally depends on the capacity of the encoder which you're using instead of the decoder. So this is the open pose representation of it, and then it tries to use that to generate this image. So yeah, basically the idea is you use a reference image instead of the regular prompt which you pass for the other diffusion models for generation. Yep, I think. Yeah. So other thing.
So correct me if I'm wrong here, but if we are trying to really make the concept very, let's say, basic, what we're trying to do here is the reference image acts very similar to a prompt.
Yeah.
Like it'll end up being in the in a similar latent space representation, and that's what we're gonna use to condition the output.
Yeah. Yeah.
Got it. Thank you so much.
Yeah. I mean, it would be relatively longer if you wanted to pass a text prompt,
right?
One of these things. So
right.
That's the kind of thing which they were saying. Like,
also, I wonder
Yep.
with the control input, like what we drew and everything.
Yep.
So basically, what we're drawing on the canvas, it's basically just being converted into an image and being passed to the encoder to get a representation. Correct?
This itself is an image.
Yeah,
This-
exactly.
okay, yeah.
The
Yeah,
control
I get it.
input
Yeah,
is an image.
exactly.
So
Yeah.
that's the represent.
Yep.
We get the embedding representation. Got it.
Yep.
Got it. Got it. Thank you
Yeah,
so much.
exactly. Yep, sounds good. Thanks, Sudhitya. Yeah, I think that's pretty much it. If there's anything you'd like anyone would like to point out, just feel free to do so. Otherwise, we can conclude, of course.